Hello and welcome back to the MoDyPy Basics tutorial series. My name is Ralf, and in this tutorial I will show you how to determine the steady state inflow of a water tank. If you are the kind of person who rather reads tutorials instead of watching them, hop over to docs.modypy.org where you will find this tutorial series in text form. In this tutorial, we will look at this water tank and find out what the amount of inflow is that is required to keep a steady height. And to do that, we will use the steady state determination feature of MoDyPy. First, let's have a look at this tank. The tank has a given fill height that can change with time, and based on its cross-section, we can calculate the volume of fluid that is in the tank. There's always fluid flowing into the tank. So we have an inflow here, and the inflow velocity is V1, which changes with time. And we have the cross section of the inflow to calculate the volume flow here. However, the tank is also leaky. There's an outflow here, and the outflow velocity depends on the fill height of this cylinder or of this tank. And also we have the cross section of the outflow here. So if we apply Torricelli's law, we find that the rate of change of the height is the volume inflow minus the volume outflow, where we determine the outflow velocity from the height, divided by the cross section of the tank. So that is our dynamics equation for the water tank. And what we want to determine is what is the amount of inflow we need to get that to zero so that the height stays constant. And of course, for this example, we can simply determine that analytically, and we get a formula for the inflow velocity. However, for more complicated systems, this can get tedious very quickly. So that is why oftentimes you will use numerical methods for determining the steady state. And there is such a feature in MoDyPy, which we will use now. But first, let's have a look at the definition of a steady state in case of MoDyPy. We want to find an input and a state in which the state will not change, and a set of conditions on the state and the inputs are fulfilled. So we have the derivative of the state, or a subset of the state, that is also possible. We have the derivative of the state equals 0, which means the state will not change. And then we have an arbitrary or almost arbitrary vectorial function of the state and all inputs, which means we can also calculate all the values of the internal signals. And we say that components-wise, this vector shall be greater than or equal this lower bound. We can also define upper bounds here by simply inverting the signs on both sides. So if we have something negative here, so that decreases with increasing values of some function, and we have a negative bound here, then that establishes an upper bound. However, in MoDyPy, it's much easier. You can explicitly specify arbitrary functions and their lower and upper bounds in the configuration for the steady state function. So let's have a look at the code. I have already coded the basic model of our tank. And the only thing that I've done differently than you might have done based on the previous tutorials is I have declared the inflow velocity as an input signal. We don't know the inflow velocity. Actually, it's one of our unknowns. So we cannot define a signal with any specific value here. Instead, we want to instruct the steady state algorithm to determine the value of that inflow velocity as it is required for keeping our height constant. And to do that, we simply declare a signal that specifically is an input signal. We get the input signal class from the MoDyPy model package. Other than that, there's nothing new here. We have a scalar state, which is the height, and we have its derivative, which we calculate from the height itself, and from the inflow velocity based on the formula that I showed you. So now we want to determine a steady state at a given target height, and that target height is specified here. For that, we need to import the steady state finder, and that is to be found in the steady state package. There is the steady state configuration and the find steady state function. And we establish a steady state configuration here for the system that we just defined. And we want to first define that all our states are steady states, but that is actually the default. If you want to exclude some state from the steady state set, then you have to explicitly do so. Look it up in the documentation if you need it. It's not relevant for this tutorial, but it's easy to find. What we want to constrain, however, is the height. So for that, we use the states property, which is a dictionary of states. So we can simply use our height state as an index here, and it has two attributes, lower bounds and upper bounds. And there we can establish lower and upper bounds for our state value. And the default is -infinity or +infinity. So we will set both to our target height, thereby constraining the height to the exact value. So here we have our upper bound also set to the target height. And we might also restrain our inflow velocity to be non-negative, so that the inflow cannot suck anything out. I don't expect this to happen, but it's a nice idea to demonstrate how to define constraints on inputs. So the lower bound for our inflow velocity input is 0, and we set that in the inputs property, which again is a dictionary of all inputs in the system. So with that, we have our problem defined. And now we want to find the actual steady state. For that, we call the find steady state method with our configuration, and it will provide us a result object. And one element of that result object is the success property, which we can print. This is a Boolean that is true when a steady state matching the conditions has been found, or false if it hasn't. We will assume that a steady state will be found. That is typically the case here in this scenario. So we just print it just for information. What we want to know now is, for example, we want to know the inflow velocity that our steady state algorithm has identified. So we print that. And we simply use the inflow velocity signal as a callable and call it on the result system state object. So the result object contains a property system state that represents the system state at which the system is in steady state, fulfilling the conditions that we have laid out here. And we will also print the theoretical inflow velocity for comparison. So that is square root of 2 times gravity times the target height times the ratio of the outflow and inflow cross sections. And just for good measure, we will also print the derivative of the height. In this state. It should be 0 or close to 0. And we will also print the height and check if it matches our target height. So let's run this example and check if the outputs are correct. Oh, I have to put this in squares. So here we see it was successful and it has identified this inflow velocity, which equals the theoretical inflow velocity to 6 digits after the decimal. We see that our height derivative is close to 0 and our height is very close to the target height. So that is how you identify a steady state in MoDyPy. Stay tuned, and the next and last installment of the MoDyPy Basics tutorial series, we will look into how to linearize systems, for example, at a steady state, which is important for designing linear controllers for nonlinear systems. So stay tuned and see you soon.